Okay, so now comes the most important aspect and most interesting developments which happened in the field of object detection. This is like moving away from two stage, or rather compress the two stages and come up with an end-to-end convolutional neural network for object detection, and we call it single stage. And that is also important, and because this move was more driven by real-time lightweight neural networks in that sense. Okay, and the most interesting aspect which came, or most interesting model which evolved out of this concept of single stage, is known as you only look once, or the famous YOLO series of architectures. So I have a slide which kind of tells you the revolution of YOLO models. So many models evolved, and now we are at YOLO version 11 as of we speak, because September 30th they released the 11th version. Of course, it's not done by one person, it's a joint work. The first one was done by Redmond et al. And we will also briefly see what is this network about. But the fundamental idea is very simple. You take the image, okay, and you divide this image into S cross S grid. Okay, so that's the concept. So first image, you divide it into S cross S grid. Okay, this S can be like 7 cross 7. So you divide the entire image. So if it is 256 cross 256 image, you divide it into groups of or totally you divide it into like 7 cross 7. Okay, so that's the idea. Okay, and then in each of those you will do kind of region proposals, or you will have each grid kind of predicts some number of bounding boxes, let's say b bounding boxes. Okay, so you have S cross S grid and you have b bounding boxes in that sense. Okay, and then each of these grids will also have a classifier probability. For example, here you can see these grids are all predicting the dog in that sense. Okay, you can see here, and this is of course the background class, and this is predicting the car, and this whatever remaining is predicting the bicycle. So you can see that in the class probability map here. Okay, so the model or the idea that they are trying to pursue, or they want to design a neural network such a way that the image is divided into some S cross S grid, basically S divisions, the total image, and each of those grids will have bounding box predictions, maybe b bounding boxes per grid. So this is a number you can basically tune. Okay, for example, b can be 2, so 2 bounding boxes, so depends on this number. So if it's very large, then of course we need to reduce the number of bounding boxes, because the group of pixels is very small. And for each of those, in addition to the b bounding boxes, we will have a classifier label also. Okay, and then what we do is we have a neural network which will kind of predict that. So basically it will have S cross S cross b. So this is kind of what they are going, b into 5 plus c. Okay, I'll explain what is this. Okay, S cross S we already know it, those are the grid size. B we already know it, per grid what is the number of bounding boxes. And 5, what is this number 5? 5 is basically that numbers, you have x, y, height and width, and at the same time we will also have a confidence score. How confident is this prediction? So let me put that as confident. So that is why we have 5 values here. So this is a confidence score for the bounding box prediction. Okay, and then x, y, h, w are the sender points and the height and width of the bounding box. And then of course the other things you already know it, and then c is basically the classifier. So this is the expected size of the output. Okay, that's very important to notice. So in the case of all the models that we have discussed so far, it is the classifier plus the bounding box. And if it is 1,000 class problem, of course this will be a 1 cross 1,000, and of course one class will be added for the background, and then followed by 4 for the bounding box, right? This was the model that we followed so far. Now we are deviating from it with the YOLO, because we wanted to compress everything and come up with an end-to-end solution. So the solution is you divide the entire image into S cross S grid, and then each grid will predict you B bounding boxes. Okay, and then each of the grid will have C classes as well. and each bounding box of course will have 5 coordinates. 4 we already know. The other coordinate is basically the confidence score. Okay, so I hope it's pretty clear to all of you. Okay, so now let's look at the model. Okay, so this is a very first YOLO model, so we can say it as YOLO version 1, and I highly encourage, I think we will try to do this in the lab as well, so from scratch. Okay, so this model is very simple if you think through. So the concept, I think this is we already explained. So you divide the image into S cross S grid. So the size is 7. For example, I think the original model had 7 as the grid. So you divide, let's say the starting is 448 cross 48. You divide that into 7 cross 7 kind of concept. And then each one will produce B bounding boxes. The first one had B equal to 2, which predicts 5 values. That's important. The confidence is something which we introduced in the previous slide. The others are known to you already. And then each grid will also be having a class, okay, C. And C is equal to 20 in the first model because it was using a famous data set, which is the Pascal VOC data set. We will use the same in the lab as well, which is kind of 20 classes. Uh, uh, you can also visit this site and see for yourself. And that's the reason why they chosen C equal to 20. So the output by the formula, it will be 7 cross 7, then cross B is basically 2 into 5 plus we have 20. So it will be 7 cross 7 cross 30, and that's exactly the output. So this is a very interesting, because typically you have the output a vector, right? If you remember, we have the classifiers followed by these bounding box parameters. So it was a vector. So maybe I'll take the ImageNet example. So you have 1001, one is the background class, plus 4. So it will be approximately 1 cross 1005, right? So that was the dimension that we were kind of playing with earlier. But now what is going to happen is basically the uh, output itself is no more a 1D kind of thing. It is more than that. It is actually the grid prediction with this 30. The 30 dimension is inclusive of this. That means the 5 bounding boxes uh, parameters plus 20 class parameters. So this is actually the dimension which has the classes as well as the uh, confidence score plus the uh, bounding box parameters. Okay, so that's the idea, and that is repeated for each grid in the image. Okay, the rest is all simple. Actually, if you see, the rest is the typical convolutional neural network, and you are basically going from this size gradually. I mean, at the initial stage, this sudden jump, because you can see it's a stride of 2 and then max pole of 2. So both are applied. So again, this follows the same concept of, um, if you remember our classifier class, the neural networks like AlexNet, GoogleNet, etc. had a heavy reduction in the image resolution at the start. This was to save the computational cost. So same is followed in this work as well. So you went from 448 cross 448 immediately to 112 cross 112, and then it's more gradual, I would say. So 56, 28, 14, 7, and that 7 is kind of left, and then you have 7 cross 1024. So this is a typical network, I would say. It's not nothing new, except that they use the 1 cross 1 convolution. I hope all of you remember the use of that, just to change the number of channels, right? Okay, and then you have a fully connected layer. This is the interesting part. So you're collapsing this to a fully connected layer of size 4096, and then you are reshaping it. So this is flattening and this is unflattened kind of setup, and unflattening to the desired this one. And this is not really any feature map, but it is actually the classifier plus bounding box head here. And then of course it is multitask loss, as previously we have discussed, the same kind. And the network is inspired by GoogleNet because of this 1 cross 1 and 3 cross 3 simultaneous convolutional layers and all, and also the heavy reduction. It's inspired by GoogleNet in that sense. Okay, now let me remove all this. So 7 cross 7 cross 2. Okay, so that's those many bounding boxes, because 2 is the bounding boxes, they result in 98 bounding boxes per image. And of course each bounding box has these 30 parameters that let's ignore for the moment, the 20 classes plus the 5 bounding box related parameters. But 7 cross 7 cross 2, that is basically an important parameter. So 98 bounding boxes per image. Okay, so that is much higher than 2000 proposals, sorry, much lower than 2000 proposals which was there in RCNN. So of course you expect a reduction in accuracy, but much faster speed here. Okay, and then this will be overlapping, this will also have overlap. And what is the technique that we generally use to avoid the overlap and come up with unique bounding boxes? Don't forget that it's the IOU concept, right? Intersect over union, and you see the intersect over union between subsequent boxes, and if they overlap too much, we will kill the one with the least score, right? So that's the idea. So don't forget that. Okay, so this is an important point to note, this 98 bounding box. Okay, so that is all about YOLO, and YOLO triggered a series of work in this direction, the single stage work direction. And this is a summary of YOLO in that sense. This is a normal convolutional network which will bring down to a fully connected layer, and then finally this guy. Okay, and then it will produce 98 detections per class. And of course you use the IOU score and concept known as non-maximum suppression, we discussed it earlier, to come up with the final bounding boxes. Of course there are a lot of thresholds you can play with, like IOU threshold is a key threshold here to come up with the non-maximum suppression. It was able to kind of get 63.4 MAP, mean average precision, hope you remember, and this with a frame rate of 45 frames per second. That means it's really real time and it's really lightweight as well. Okay, so that's very important. That's the motivation for this. Okay, and inspired by this, then came another network which we call a single stage detector, SSD. And the key concept or the key important thing that they uh, introduced is the YOLO has a problem here, because it is assuming the image to be like 7 cross 7 grid or whatever, S cross S grid, and each grid is giving a bounding box. But then there is a problem, because the bounding boxes may not be of the same size, or the objects that we are interested in may not be occupying the same number of pixels. So for example, the dog is much bigger compared to the cat here in the image, or if I want to segment the book, for example, it's even smaller than that, right? So that is not really taken care into the YOLO framework, and this is possible to be tackled if you have feature maps at different resolution. Okay, so that's something which I mean basically here also you have the feature maps at different resolution, but they didn't do any kind of usage of that towards this particular idea where the object is of different size. So here for example, if you use this feature map of size 8 cross 8 to kind of put a bounding box, it can put a bounding box on the cat but not on the dog. The dog on the other hand can be put on a 4 cross 4 feature map. Okay, a much bigger feature map which is maybe at a global level, it's able to kind of map the full dog completely. Okay, so that's interesting actually, because uh, this concept is actually interesting, because the uh, I would like to put this way, a small subset, a smaller or the same concept of that image resolution, where the the bigger or the deeper layer will look at the global picture and a closer, because you see here this will be a closer to the image, so it looks like a more local kind of feature, and that's nicely used, and that is what we call a single stage detector, SSD. And the concept also is very simple. So it's basically using the VGG backend. Okay, and then you can see over here you how the detections being done on each and every feature layer as well, most of the feature layer as well after some point. Okay, so you have uh, the same concept, of course, the classes plus 4, there is no confidence score here, so 4 values plus classes, that is being done on multiple layers at multiple resolution. That's a critical fact. A total, if you sum all these up, you get around 8732 detections per class at various dimensions. So here, if you see, it was 98 per class, but everything was kind of 7 cross 7 uh, on the grid, right? So instead of that, here you have at multiple resolutions, and you can see like this, right? So 38 cross 38 we have the detections, 19 cross 19 we have the detections, 10 cross 10 we have the detection, 5 cross 5 we have the detection, 3 cross 3 we have the detection, and even this one we have the detection. So at multiple resolutions we are kind of putting the bounding box, and then use the non maximum suppression to kind of suppress the unnecessary. Of course, when you do this projection, it has to be the same size of the image, which is taken care internally, because this guy, for example, is only 3 cross 3. You need to resample it to the same size of the image to kind of compare across to do the non maxima suppression, right? Okay, so the key thing, the key takeaway here is YOLO didn't consider multiple resolution. However, the SSD considered the multiple resolution. Okay, and this concept where you kind of use the features at different resolution is also known as feature pyramid, because if you stack them together it will look like a pyramid, right? Because your resolution is kind of increasing. So this is the deeper layer and this is the earlier layer, right? You go deeper this way, so it's like a pyramid. There is a feature pyramid network as well. I'm not discussing about that. If you are interested, please take a look at it. But this guy is kind of utilizing that flexibility. Okay, and one key thing which I missed, I think, explained so far is the irrespective of two stage or single stage network, there is a backend network, right? Deep convolutional network, which backend used at the backend, and you can use any of the ImageNet trained network. For example, it can be VGG or the ResNet or the Inception module, whichever you feel you can use it. So there's a huge flexibility there, and based on the backend, the results can be different as well. So there is a lot of variability in that aspect as well. I think I have a slide which consolidates all these variabilities in object detection. Okay, I hope the takeaway is very clear here. Okay, and then came the YOLO revolution. That's why I told it has been a revolution, because YOLO was introduced in, we already discussed about YOLO version 1, it was 2015, and literally every other year, or at least 2 to 3 years, even in some cases within a year, so many evolutions have come. And latest is actually YOLO 11, which was released very recently, last month, September 30, 2024. Okay, so I was actually using this for some work not very far away. It's just 6 months ago I was using this and was getting very good results. Okay, but now we have YOLO version 11, which is already there, and good part is like it's a joint work. It's not like one person or one university is doing. You have university UW which started this, and kind of till version 3 it was kind of supported, and then Ultralytics, it's kind of an effort which to combine YOLO into a big framework. So we can call YOLO as a foundation model in object detection, because it solves the purpose in many applications. Ultralytics as a web page, will go there shortly. So it is kind of maintaining the YOLO now. Some of them was not actually. So Baidu also contributed, for example, here, and you can say Ultralytics is kind of, they are not maintaining everything. So 11 is there, version 8 is there, then 5 is there. These are stable versions, I would say. 7 was also good actually in one sense, a lot of popular. Okay, and we are going to do a deep dive on YOLO version 8 very soon. Okay, but before that, where is YOLO applied? So I taken this from a recent paper, a review paper, and you can see a bibliometric network visualization of the applications of YOLO. So almost all places, like many traffic examples like license plates, autonomous vehicles, traffic signals, vehicle detection, rail detection, aircraft defects, fruits, agriculture, face recognition, diagnostics like medical applications. So radar, for example. So many places. It's not natural images alone. you have infrared images, you have ultrasound images, you have medical images coming many places. YOLO has been used, and that's why we can safely call YOLO as the foundation model for object detection in that sense. Okay, and then this is kind of the comparison. So COCO is another data set which has been used for just like ImageNet for the object detection comparison, and you can see the uh, comparison of various versions of YOLO, and within a version of YOLO, for example 11, you have multiple versions. So this is a very lightweight version, and N stands for very lightweight, S stands for small, M stands for medium, L stands for large, and X stands for extra large. So of course accuracy is better, or the average precision is better as we go for a higher version of YOLO, or a complex version of YOLO, but the speed is best for, so 40 uh, sorry, the speed is here. So the speed is, so this is the time taken for per image, millisecond per image, right? So this is better, this side is better in terms of speed. So you can see 11n is better than all other cases in terms of precision, average, mean average precision, but at the same time it's much faster. And in fact, if you go to the Ultralytics web page, you can even, they have a kind of a uh, play box as well. I think let me just go there in a moment. Sorry, it is not Ultralytics web page, but the RoboFlow web page. They have an interesting playground where you can compare the YOLO models. I'll just quickly show this. Okay, so this is the playground, and you can upload any image, and you can see here. So the comparison. So this is by version 8, and this is by version 9. So you can see the ported plan was missed in version 8, which is picked up, and also the localization is better. And even here, so broccoli was not detected, and now you have that as well. And this is 10. Again, you can see some of them got missed, and this is 11. Okay, so some of them miss. So you can compare actually the versions, and in fact, if you go by this, I think V9 appears to be like the best, or version 9 appears to be the best in terms of the results, accuracy results. So you can upload your image here and then check for yourself. Maybe let me quickly give you an example. So maybe an automotive image, a car. So let's run this. And I think this is told here, this is basically trained on COCO classes. So you need to see the COCO class. Car is definitely there. So you can see V8, and you can see the localization improvement as well. Okay, great. So you can see V10 has a better localization, and V11 is more confined as well. So you can do this comparison in this web page. Okay, thank you.